Hey, Honors Physics, this is Mr. Hausman. We're going to take a look at charge movement today. However, we're going to sneak in just something that we may have discussed in class, but I want to fully explore. This is actually best explained through maybe some videos that we will be seeing in class. But there's two other types of materials. We've already been introduced to conductors and insulators, probably in past science and then reiterated here in physics. But these two other types are semiconductors and superconductors. And one of those is incredibly rare and exotic, and one of those is everywhere in our modern world and are the key components in modern electronics. So it kind of seems like a shame that we don't introduce the most common type of material. They're not conductors, they're not insulators, but one of the most common types are semiconductors, or at least they're very prevalent. So a superconductor first. This is the rare guy. They are also maybe exotic, but what they have proven to be able to do when they are fabricated, they're not found in nature, is that they exhibit zero resistance to electron flow. So it's almost like a frictionless conducting pathway. So they're, after all, superconductors. And one of the huge things that they are predicted to be able to do is to conduct with no loss of energy. So where would we use these? Well, there is a dream and actually considerable research to make superconducting wires that could move electricity from regions of our country where it's very easy to make abundant carbon emission-free electricity, such as through solar power in deserts or hot climates where they have a higher concentration of sunlight, and move that electricity throughout the country. Or even hydroelectric power or wind power to move it across the grid with no loss of energy. Well, what I mean by rare is that they are, of course, made in laboratories. And if you saw one, you'd probably say, oh, it looks like a ceramic. And they are in the family with ceramics, and they're made of some pretty exotic elements. Yttrium, barium, and copper are among some of the most common elements, yttrium, barium, and copper oxides, as it turns out. But there's one requirement. Superconductors only exhibit this zero resistance below a critical temperature. If they get cooled down to a cool temperature, they go into a superconducting state. Above that temperature, they're just a piece of material. They don't conduct very well. And so what is that critical temperature? Well, the goal of superconducting researchers for about the past 30 years has been to get that temperature to be room temperature. And they even have published papers that say, oh, we got there, room temperature. Negative 70 degrees. And you're like, what? That's really cold. Well, when they started this research, they started with superconductors, that had to be negative 200. So considering the range, that's Celsius, of course, and considering the range, they've made a lot of progress. And they keep making progress on superconductors. But I'll be candid, I am not on the cutting edge of the research on superconductors, but when I was in high school chemistry and physics, my chemistry teacher said, they're coming, they're going to be here, and it's always 10 more years out, 20 more years out. Now, they also exhibit some really cool properties having to do with their magnetic fields. I'll show that in a video. Next up, semiconductors. Semiconductors, as you may have heard, the semiconductor industry is an entire field of research that has led to basically the creation of transistors. Semiconductors make up transistors. Transistors are what have been miniaturized to put into the brain, the CPU, these chips that we use for everything from processing information, taking in sound. The number of transistors that are going into you hearing this from my voice is in the billions. Each device can have billions or trillions of transistors. So what is a semiconductor? Well, let's get to the fundamental materials. They are made of semi-metals. Semi-metals are on your periodic table. They're on the staircase. Does anyone remember hearing about on the right side of the periodic table, not the far right side, but basically between the nonmetals and the metals, there's a staircase of elements like silicon, like germanium, and like gallium that have these properties that are a little bit metallic, a little bit non-metallic. And I may not have put them in the right place, but the point is these elements have to be on this adjacent line where it's not a non-metal and it's not a metal. It's a semi-metal. And based on how you treat those elements, they're actually poor conductors under some conditions, but then you can add things to them to make them more conductive. So they're not great conductors, they're not great insulators, they're in between. Well, if you take your silicon and you do something called doping, you can turn it from a conductor to an insulator, and that becomes a switch. You can actually change it from a conductor to an insulator, essentially by an electric current, a very small control current that can turn a switch that can control basically what's called binary calculations on and off. And that's how information is processed, really, is switching of information. I certainly encourage you to take more advanced physics and electronics courses to kind of examine how those chips actually work. And electrical engineers are kind of the expert at that because they're constantly trying to improve the transistor. And something I've heard of recently, just to give a little enrichment, is that silicon has been the element for like decades. Arguably since the computer chip was invented back in the 40s and 50s for the very first computers. But in the 21st century, in the past 5 to 10 years, research labs and actually manufacturing companies have realized that, not germanium, made a mistake there, gallium in a form called gallium nitride is actually way more power efficient. So when you're trying to do switching or control circuits, they are finding that they need to find new sources of gallium because it's allowing chips to be more efficient. And these are available. You can buy these. It's not in your CPU yet. It's not in the brain of your phone device or tablet or laptop. They're used in power supplies where power is really efficient. So I bet the next time you buy a device that has a charger, you're going to notice that the plug is getting smaller and smaller. And that's sometimes due to the fact that they are using more gallium in their power supplies. Okay, let's keep going. So those are two really fascinating fields. We'll see some videos on those in class. Now let's talk about charge motion, because in order to do the next assignment, you're going to need to know about grounding. Okay, so all of these below are ways that charges can move. And basically, grounding is taking a charge and making it neutral. So grounding means to make neutral. Neutral, again, means zero charge, right, overall. And how do you do that, right? You're trying to rebalance the protons number so it's equal to the number of electrons. And how you do it is you make contact with ground. But ground is an expression that originally meant literally the ground, the earth, but it's really any object that's large enough with a large electron reservoir. Supply, right? So your body can be a ground, and it's pretty good at taking away charges, right? So typically you take a charged object, this is a metal sphere, and it's got a whole bunch of charges on it. Let's make it negative. They're on the outside skin of the metal. And you touch this to your body or maybe to the earth through a wire, right? You have to have a pathway. It could be your car and things like that. And what's going to happen is, see this, all these extra electrons that are on the sphere? They are going to travel away from the sphere, and they're going to go to the ground. And how many will go? Well, they don't all go, but they go until you have become, the object has become neutral again, okay? Now, there's another way of doing this. What if this same charge, and I'm going to use my eraser, and I know that's not really fair, you can't undo what you just drew. What if the charge, of that object is now positive. What if it previously lost electrons? We also have to erase this part. So you still can ground a positive object. There's the symbol for grounding. It's that inverted kind of pyramid shape or triangle you see. But in this case, you say, well, I get it. The protons, the positives, will just move through the wire. Protons cannot move. So in this case, remember this is a reservoir down here of charges. Electrons can either move into the reservoir, or in this case, the electrons will move out of the ground or out of the reservoir, and it will make that sphere neutral. How many electrons move? Just enough to make it neutral again. So grounding can be two directions. It can be to take or give electrons. Okay, let's go to number 2, friction. Friction charging is the rubbing of two surfaces. And now it creates, right, opposite charge. How do you get opposite charge? Well, you take something like fur or wool, even the hair on your head, and you take something like a black plastic rod, a BPR. We have these, we'll use these. They're made of plastic, black plastic rod, and you rub it across the fur or your hair. It could be a balloon, it could be anything plastic, quite honestly. And in this case, the electrons will be removed or ripped off, literally by the force of friction. They will move from the hair, the fiber, onto the black plastic rod. So the BPR takes electrons by friction from the fur, and the fur or the hair, the fiber, gives electrons. Well, if you take electrons, the black plastic rod has just achieved a negative charge, and the fur or the fiber is now missing electrons, so its net charge is positive. So friction charging always creates opposite charges, creates opposite charged objects. Now, you can't rub together any two materials. There's something called the Triboelectric Series, or Triboelectric, and it's a published list of materials where it ranks who is the most eager, what material is easiest to remove electrons, which one takes, and it has to do with ionization energies. The higher the energy demand to remove it, well, that's going to be low on the scale. So as long as you are rubbing two different materials. Now, the catch here, though, is like it can be really different. You could take this same fur or silk or other fiber and rub it on another material, and the electrons can go the other direction. But I want you to learn that if it's a fiber like wool, like polar fleece, like hair, like dog fur, fibers like this, natural fibers or even synthetic fibers, they tend to give their electrons up easily to things like plastics and rubber. That's going to be the most common example. But the key idea here is that you always get opposite charge. The third way to move charge is conduction. And conduction is maybe a word that you're more familiar with because it's related to conductor. But the actual process of conduction, a little bit more complicated than you may realize or more subtle. So conduction happens when two surfaces, right, that are both conductors make direct contact. Not rubbing, just touching. So here's an example of it. So you've already heard about in class these things that we kind of use as samples. This is a metal sphere, and it has acquired, right, it's on an insulating base, and it has acquired some negative charge. Okay, maybe it's -6 or something like that. And right next to it, you place a neutral sphere, right? But you keep it about an inch away or so, right? Again, it's also on an insulating base. It's neutral, so it has a balance of charges, right? The number of positives equals the number of negatives. The source one, right, here's the source, it has a net negative charge, and that's obvious. Well, the moment you put those two spheres together through direct contact or conduction, you are going to get a transfer of charges. And you might say, oh, I get it. So the 6 electrons move from the source to the neutral object, metal sphere. And that's not quite what happens. What happens is if this is a -6, the electrons move until there is a balance. There's a net movement, right, from the source to the sink. But what you end up with is both objects get the same charge. Well, not only are they both negative, but their Q values would be equal to each other. Q1 and Q2, right? Let's put a 1 equals 2, would be the same. So if -6 is the source, well, during contact charging or conduction charging, both would take a charge of -3. So they both take the same charge. So kind of a little note is they're both negative. Now, what if the source was positive and you touch it to a neutral object, a neutral conductor? Well, it's going to move the electrons. The charges are going to move the other way. We'll do an example of that. But the net result is if your source is +6 and you then have 2 objects touch, well, they are still going to have the same charge, but now they're, of course, going to be positive and positive. So that, just a reminder, I'm recording at school in the middle of the day. So that's conduction. Direct contact between 2 conducting surfaces, and we get conduction charging, right? It looks like sharing of charges, essentially, is what it comes down to. But both take the same charge. In friction, remember, there's a major difference. There has to be physical motion across the surface, like repeated rubbing, and you get opposite charges. Okay, we're going to jump down to induction, because as it turns out, friction, conduction, and induction are the 3 ways to create charge in a new object. We'll talk how polarization is different, but friction, conduction, and induction. So induction is probably the most complicated, but you'll get it. It's a non-contact method of charging that happens in several steps. So the first step is that you have to have a source. We'll draw that in just a minute, right? So there's a source charge. And we'll do a visual of that. In this case, right? Sorry about that. I had to do a quick edit due to a error with audio recording, but let me pick up where I left off. So as we know, induction is this non-contact method. We have to first visualize a source charge. So in the picture below, you see a person's hand holding a balloon. So let's do that. Let's use a balloon. We've been using kind of red and kind of the universal symbol. It's on a string. And that source charge is going to trigger some events. So let's make it a negatively charged balloon. Now, what are we going to induce the charge in? Well, let's take a neutral conducting sphere sitting on an insulating base. And it, of course, is starting off neutral because, we previously maybe grounded it. So that means the number of protons and electrons is balanced again, neutral. But as soon as this source charge is brought close to this metal sphere, 2 to 3 inches away, 5 inches away, but not a millimeter away. If you get too close, charges can actually move by jumping through the air. It takes a lot of energy, but you want to be a little ways away. And what's going to happen is that the charges inside the metal sphere are going to start to feel the force or the effect of the source charge. And electrons, being the mobile subatomic particle, are going to move as far away from the source charge as they can. And that's going to leave the other side of the metal conductor with kind of a residual positive charge. And we refer to that as polarized. Now, if you took the source charge away, the electrons and protons would mix back up together, because remember, the electrons don't want to be concentrated together on one side, but only if they're pushed there. So we've got a state of polarization. But that is followed by another key step. So let's draw it again. It's kind of like a cartoon panel. And what that key step is grounding or separating of charges. So you remember you've got it polarized because the source charge is still nearby, and then you come along and touch or ground, by touching with a wire or with your hand, you ground one side, and the electrons, the extra electrons, or the pile up of electrons who are trying to get away from each other, they will move down into the ground or the reservoir. They're moving this way, and the net result at the end is that the metal sphere, because it now was polarized and then grounded, has a net positive charge. And we're exaggerating, did all of the electrons move away? No. But the net charge is positive overall. And it's kind of shown in here with a conductor. The soda can is acting like the metal sphere. And I know it's really hard to see, but you maybe notice that the electrons go running to the far end, and therefore one end is polarized. That's not induction, though, until you make that separation permanent. And here's how we do it, by grounding. Now, could you have touched the other side of the sphere? You could. But one of the take-home messages is if the source charge is negative, then the final charge of the induced charge is oppositely charged. Usually, opposite charge. So if the source is negative, you are going to push the electrons away, then you ground those electrons, and you're going to have an oppositely charged sphere. Could you reverse this entire process? Could you bring a positively charged object near the same exact neutral object and reverse the polarization? Would the electrons move to the near side and the protons would move away? Yes. But if you ground it and touch the electrons, now they'd be over here, you'd have the same outcome. So you can kind of do it with either source charge, but if you do that, you're going to be left, again, if you touch the same side, you're going to create the opposite charge. Now, interestingly, I use the word polarization or polarized in my concept of induction, and yet we skipped it. So let's finish off with polarization. Polarization is nothing more than a temporary rearrangement of charges. And how does that happen? Well, it's always due to electron movement, and it's due to an external charge. So it's almost like it's the first half of induction. So let's examine that. Let's take that large metal sphere, which is a great kind of hands-on example. We'll see it in class. And you bring a source nearby. It may not be drawn to scale, guys, but there's a rubber balloon that's been rubbed on some fleece, on some wool, even on your hair, and it took some electrons from that fur. That's by friction, and now we have set up, right, basically some charges nearby, and now the neutral conductor will experience charge polarization, right? Polarization is temporary, and it is the movement. And it can be at the small scale, like you could actually have it in insulators. The charges really, the electrons can't move, but the molecule can pivot and move the electrons from one side of an atom to another. In this case, it's a positive source charge being brought near a neutral insulator, but do you see how the charges down here in the corner are showing polarization? And some people refer to that as induced polarization. They mix the words together. But polarization, how it's different is that it's a temporary rearrangement of charges. Induction is a permanent state of charging that is non-contact, and it happens in several steps. Bring a source charge near a neutral object, causing polarization. The polarization is followed by grounding, and now you're left with a charged object. So overall, the summary is 3 ways of charging: friction, conduction, induction. Grounding is the opposite of creating a charge. It's actually removing a charge by touching a source of electrons, a reservoir. But remember, grounding can be either a take or a give of electrons. If it's a negative source, you take the electrons away. If it's a positive source, the electrons go in, but you make it neutral. Friction is a rubbing, not a contact. It's a rubbing of two surfaces. One takes electrons, one gives, and the key idea here is that they become opposite. Conduction, it's contact without friction, but it happens to be with conductors and you take the same charge. Induction, non-contact, 3 steps: source, polarize a neutral object, ground that neutral object, separate the charges, and you have a charged object. So a little bit longer, but a lot of ideas that we'll explore over the next few days. Good luck on page 8, 9, and 10. It starts right here. Here's where page 8 starts, where you're using your vocabulary. You're filling in kind of some blanks. Some of them are multiple choice questions. Here, this is a narrative, step A, step B, step C, and I'd like you to kind of draw in the charges that you kind of see or how they'd move, and then answer the questions about what would have happened in this cartoon. So A, B, and C is like a time lapse or a narrative. It's like a simulated experiment, and I want to see if you can predict what would happen. 9 is similar but different. 10 has the same top, but has different examples or considerations from below. And then finally, page 11. Good luck. We'll definitely go over these guys in class.